Next, we will discuss Slaughter's rule. Now, this rule provides the numerical values for the effective nuclear charge in many electron atoms. It was formulated by John C. Slaughter in 1930. I'll take the laser pointer here. Sorry. So, according to this formula, Z effective is equals to Z, which is the atomic number of that molecule, minus S. S is the Stirling constant. So, how to determine the S? So, to determine the Z effective, we already know the Z, the atomic number of the atom, and we just have to determine this shielding constant S. So, firstly, electrons are added according to their principal quantum number. Remember, not following the Aufbau principle. Okay, they will just simply grouped according to their principal quantum number and taking S and P in the same shell. So the order will be like that: first you have 1s, then 2s and 2p in the same shell, 3s and 3p will be in the same shell, and then will come the 3d. So according to the Aufbau principle, after 3s and 3p, 4s will get filled, right? But here we are not following the Aufbau principle. Okay, in case of Slaughter's rule, you don't follow the Aufbau principle. You just arrange it and then calculate. So 3s, after 3s and 3p, you will put 3d. Then again you will put 4s and 4p together. Then you will put 4d. Then you will put 4f. So d and f are separately. Only s and p you can put together. Okay. D, F, G, these things you will put separate. Then you will again put 5s and 5p. Then you will put 5d and then 5f. Now let's see the quantitative value of this shielding constant. Okay. So the shielding constant for each group determined as, the first one is an amount of 0.35 from each extra electron within the same group. So if the electron for which you are counting the shielding constant, it is sharing the house with other electrons, so you have to calculate 0.35 for the other electrons. Okay, and 0.30 for only 1s electron. In 1s it will be 0.30, other than 1s it will be 0.35 from the same group. So these ones are called actually groups. This one is one group you have created, this one is another group, this one is group. You have grouped the electrons for determining this shielding constant. If the electron which is to be considered is in ns or np, this group, so an amount of 0.85 from each electron with principal quantum number n-1 and an amount of 1 for each electron with the principal quantum number n-2 or lesser. Now next, if the considering electron is in D group or F group, an amount of 1 for each electron, those having smaller principal quantum number and same principal quantum number but smaller azimuthal quantum number or different group. Now we will try to understand it from the example, taking the example. So first, this is the summary, or this is the chart. Here are different groups, and here you can see for the other electrons in the same group what will be the shielding constant value. From other electrons in the same principal quantum number but different azimuthal quantum number, from other electrons with n-1 quantum number, and from all other electrons up to n-2 quantum number. For 1s we have maximum 2 electrons, so we have just 0.30 from the other electron in the same group. And for other ns and np we can have total 8 electrons here. So for other electrons in the same group you have 0.35, and for other electrons with n-1 quantum number you have to add 0.85, and all other electrons up to n-2 quantum number you will get 1, shielding constant as 1. Similarly for D, 0.35 from the other electrons in the same group, 1 from the electrons that are in the same n but other azimuthal quantum number, means in the S and P, and 1 from the other electrons whose quantum number is less than n. Similarly, from the F group, if there are electrons in the same group, means more electrons in the F, that time you have to add 0.35 as a shielding constant. From other electrons in the same principal quantum number but different L, means in the D or sp group, you have to add 1. And similarly, from the other electrons in the different quantum numbers, you have to add 1 for the shielding constant. Now we will take an example and we will determine the shielding constant for all the electrons of this iron. For this I will choose the pen. Yeah, see, so for iron, this is the electronic configuration 1s2. So not this is not the ideal configuration, this is actually how you write to determine this shielding constant. First you write 1s2, then in one group you add 2s2 2p6, another group you add 3s2 3p6, then you write 3d6 and 4s2. Now we will determine the shielding constant of these 4s electrons. So here we have 2 electrons. So for 1 electron, if we calculate, so there is only one more electron in this 4s group, right? So from that electron we will get 0.35 shielding constant. That's why 0.35 into 1. Now from these 14 electrons, they have same n, same principal quantum number but different azimuthal quantum number. So we will get 0.85 into 14. So this much will be the shielding constant value from these two groups, this one and this one. So this one electron, this coming from 4s, that is giving 0.35. These 14 electrons, those are coming from this 3s2 3p6 and 3d6, that is giving 0.85 each. And we have 10 more electrons in this 1s2 2s2 2p6. We have 10 more electrons. These 10 electrons are contributing total 1 value. The total shielding is depicted as 1, and if it is less than 1, so that means it is not shielding totally. Okay, so if we calculate, so we will get S as 22.25. Now our atomic number is 26, so Z is 26, and if we do Z minus S, we will get Z effective to be 3.75. So 3.75 is the Z effective in this 4s electrons. Means originally in the iron, so if this is the nucleus, I will just shade it. So in the nucleus we have 26 electrons, right? Now after that we have different 1s 2s 2p 3s 3p 3d 4s. So we have all these electrons. Now just assume if it is 4s electrons here, and we have all other electrons here before these 4s electrons. So these 4s electrons, each electron, they will think that there is only 3.75 number of protons. So actually we have 26 number of protons. So that there are 26 number of protons, and the 26 protons are attracting these electrons, but the inner electrons, they have shielding effect. So they are shielding the attraction of these protons. So that's why this 4s electron, they will think, or they will get the force that only 3.75 protons are there in the nucleus of iron. So that much attraction these 4s electrons will feel. Now let's come to the 3d electrons, and if we determine the shielding constant of 3d electrons. So for 3d electrons, there will not be any contribution from 4s. Okay, so we have to consider the electrons which are before 3d or in 3d. So from 4s there will be 0 shielding constant. Now in the 3d electrons we have 3d6, 6 electrons are in total. So each electron can see 5 more electrons. So 5 more electrons, and they are giving shielding constant 0.35. So that's why we have to multiply 0.35 with the 5. So this, from this 3d6 we get 0.35 into 5, and all other electrons with the same principal quantum number and different azimuthal quantum number, this one, and here different principal quantum number, they all electrons contribute shielding constant 1. So that's why all 18 electrons before this 3d, they will give shielding constant 1. So the total shielding constant comes out to be 19.75. And if we subtract this S from the Z value, we get 6.25. So the Z effective is 6.25. So the electron which is at 3D, if the electrons are 3D, so those electrons will feel, those are much closer to the nucleus, right? So they will feel more attraction to the nucleus. So they will feel that per electron there are actually 6.25 protons. So this will be their conception, means that will be the Z effective to this 3D electrons. Now if we calculate for the 3s2 and 3p6, these electrons, so total there are 8 electrons in 3s2 and 3p6, and this 3d and 4s will not contribute anything, so we will have 0 and 0 for 4s and 3d. Now 8 electrons are there in the 3s2 3p6, so one electron can see 7 more electrons. So 7 electrons will impart 0.35 shielding constant. Then before that we have 8 more electrons in the 2s2 and 2p6. Those 8 electrons will give 0.85 shielding constant, and we have 2 electrons in the 1s. So those 2 electrons will give shielding constant 1. So total the S will come out to be 11.25, and if we do Z minus S, we get 14.75 as the Z effective. So the electrons which are in the 3s and 3p, see here the principal quantum number is same, but as the azimuthal quantum number is different, so they will have different effective nuclear effective Z effective, different effective nuclear charge. So they will feel the Z effective to be 14.75, whereas in case of 3D electrons they are feeling only 6.25. So the 3s and 3p electrons, they will have higher attraction towards the nucleus. Now if we calculate for 2s and 2p, so for 2s and 2p, all this right hand part will be 0. So we have 0 for 4s, 0 for 3d, and 0 for 3s 3p. So in the 2s and 2p we have 8 electrons in total. So each electron will see there are 7 other electrons. So 7 other electrons will impart 0.35 shielding constant, and the 2 electrons in 1s2, they will impart 0.85 as the shielding constant. So the total shielding constant is 4.15. So if we calculate Z minus S, we will get 21.85. So the effective nuclear charge is 21.85 for 2s and 2p. So these 2s and 2p electrons, they will feel that this atomic number, or this number of proton in the nucleus is actually 21.85. So that much attraction they will feel. And if we consider for 1s electron, all other contribution will be 0 from 2s, 3s, 3p, 3d, and 4s. And 1s, in 1s we have only 2 electrons. One electron can see there is one more electron. So that electron will shield only 0.3 or 0.30 just for 1s. So the effective nuclear charge will be 25.7. So the electron which is very close here, 1s electron, that will feel that in the nucleus there are 25.7 protons. So this is the concept of effective nuclear charge. So this tells that in an atom, differently positioned electrons, they will feel different effective nuclear charge, and depending upon their effective nuclear charge, they will feel more or less attraction towards the nucleus. Fine.
Hey genius, I hope you liked the video and the concepts are clear. So if you want to know more and if you want to learn more, you can go and check the periodic table and periodic trends folder. I have already uploaded 7 lectures on this topic. Please go and watch all those 7 lectures. I hope it will be very useful for you. And if you think these videos are knowledgeable, please share it with your friends and don't forget to subscribe. Okay? Thank you. Bye bye.